Welcome everyone to the second bi-weekly Breaking Science lecture. For those of you that haven't been here before, welcome. It's a series where we try to take really cutting-edge medical research and scientific literature and distill it down to a form that lay people or people with like a high school science education should be able to understand. And then of course, if you want to know more in-depth stuff, just ask me. I am a scientist. I do get paid to do science. Importantly, no one's paying me to give this talk, so the things that I'm telling you are not biased by somebody saying you need to say this or that. So any questions, just feel free to ask, but nothing's too basic, nothing's too advanced. So what do you guys already know about vaccines? Because it's something that's, you hear about in the news and in life all the time, and there's a lot of conflicting information out there. So when I say vaccines, what do you think about? Maybe people that aren't professional scientists. Yes?
So referring to the flu vaccine, I've heard some of them are called live attenuated. I have no idea what that means. And dead, I think. And then I always wondered why you can sniff one and shoot one, and what, do you get any better response, either one?
So we'll definitely cover the first point in depth in the talk. The second question is probably just people tried it in the nose and it worked. It probably has to do with whatever pathogens infect the nasal mucosa. Yes?
Well, some of them you can get for life, or it protects you for life, and then some of them are not for life. And then you have some of them you have to get boosters. I don't know why.
So that's something that we really don't understand very well. People have been spending a lot of effort trying to figure out what adjuvants you could use in the vaccines to make more robust immunity that lasts longer over the course of your life. But some pathogens, like the flu, it seems like you really just don't make memory cells that last your whole life. But chickenpox, you're protected for a long time. So it's an important question.
I thought flu vaccine or flu viruses just mutate more. No.
Their rate of mutation is fast, but it's still not fast enough. But anyway, anything else that anyone wants to add in about vaccines that they heard about or want to know about? We're going to cover a bunch of stuff. But yes?
People think it causes...
We'll address that.
Okay, good.
Autism.
Going to preface what I'm saying by saying that all of the information that I'm presenting is purely based on literature that's been published and reproduced and tested by scientists, leaving the emotional and sociological aspects out of it. So, for scientists, it can often feel like this: that there's a lot of people that think that vaccination is evil and detrimental to kids, and so they end up with sick kids. And scientists just have this syringe of facts that they're trying to inject into people, and it's not working. But it's understandable when you think about the people that are advancing the anti-vaccine cause, such medical experts as Jenny McCarthy, Charlie Sheen, Tom Cruise, and Donald Trump, all of which are pretty renowned in the medical community. I'm going to ignore largely what they say and only talk about the facts. How do vaccines actually work? Well, there's really nothing special about vaccines, admittedly. They just kind of work like your normal immune response. So you'll administer a pathogen, whatever it is, and then allow your body to mount a natural immune response to it. The reason it works really well is because usually they'll be attenuated, so weakened, or killed, so they can't establish a productive infection in you. This is much better than just giving a live pathogen, although that would also work, and certainly has been tried in the history of human medicine. Anyway, you can also, modern vaccines are using less and less of the pathogen, so just fragments of it, to really minimize the risk of you getting infected by things that you put into your body. Most vaccines require multiple doses, and this is really just to boost the immune response and expand the pool of cells that are activated by the vaccine. If you encounter the pathogen again in the future, just like if you encountered it naturally, the idea is that you will fight off whatever you were vaccinated against much more easily because you've expanded your pool of memory cells. So I put this slide up in the previous lecture, but it's relevant here as well. Floating around in, yes?
So don't babies not have certain
Until 6 months. That's a really good question.
antibodies? So then can newborns not get vaccinated?
Newborns generally aren't vaccinated until about 6 months because that's when lymphocytes start developing. Prior to the first 6 months of life, generally most of the immune system is passively given through the breast milk.
Then why are some vaccines given when you're born?
Because you do have some immune cells. You have innate immune cells. And so if you prime your dendritic cells and such with the antigens, they can then present to the cells that develop. Good. All right, so you have T and B cells floating around in your bloodstream. They are specific against many, many different things. Although you have about 10 billion T cells and B cells floating around in your body. Against any pathogen that you haven't experienced, you'll have about 10 or 100, between 10 and 100 cells that are reactive. So this is very, very small. They can be specific for tuberculosis, Ebola, the cold, E. coli, all these different pathogens that you haven't encountered. If you then encounter Ebola, which presumably would be the first time that any of us have, you'll activate the Ebola-specific T cells. They'll divide and expand. Additionally, they'll differentiate into memory cells, which are better at becoming activated subsequent times. So this is why when you get vaccinated against something, subsequent challenges, you already have cells floating around that are ready to handle the pathogen. Memory cells generally live a lot longer than naive cells, and that's how you have lasting immunity, which can last for a very long time. So I'm going to put up a little bit about the history of vaccines because it's actually kind of cool and really tied into the history of Boston very much, which is neat. So going back to 1721, which was a heck of a long time ago, you had this guy, Cotton Mather. He was in Boston. He was advocating a process called variolation. This was basically you had a patient with smallpox. You scraped off one of their pox and scraped it into somebody else, gave them smallpox, but then they would become immune to it. The idea behind this was that if you took a pox, the virus that was in the pox would not quite be as effective at infecting you as, you know, a virus in bodily fluids or something like that. Worked pretty well. 3% of healthy people were killed by this. So a lot of people were really opposed to getting variolated, and this guy got a lot of death threats over the course of his life. Needless to say, Boston became a really big city advocating the process of variolation. And papers started circulating throughout the rest of the colonies telling you how to do this. Because the cool thing about this was like any person could do it. You didn't need a doctor. 1774, Ben Franklin writes this really passionate letter. He lost a 4-year-old son that was not variolated. And he becomes one of the first parent advocates of vaccination or variolation, saying that he wished that he had variolated his kid. We almost lost the American Revolution. We would be all speaking British today were it not for smallpox. George Washington's army storms into Boston, and all the Brits that were here had been variolated, so they were immune to smallpox. So when the army came, and they were not, a lot of the troops were wiped out by the smallpox epidemic that was going on. Eventually Washington was like, hey, we should probably variolate people and make them immune to this. So he did, and we won the revolution, and, you know, long story short, we talk American. 1796, you have a British physician by the name of Edward Jenner. He's one of the first people to vaccinate. The difference between what was happening before variolation and vaccination is that you had vaccinia virus, which causes cowpox, very related to smallpox, but, you know, it happens in cows, hence the name. When you took a scab off of a cow and you rubbed it into a person, it didn't cause as much disease in the people, but it did give you protective immunity against smallpox. So this was a really good way of getting around the 3% of healthy people that were being killed by variolation, because nobody likes that. 1813, the United States establishes the Vaccine Agency, which was set up to immunize, to vaccinate any people that wanted to be vaccinated, which is kind of cool. 1863, this guy is Abe Lincoln, you may have heard of him, gives the Gettysburg Address. 4 hours later, he almost dies from smallpox, and almost nobody ever hears about it. Should have been very good. 1879, this French guy, Louis Pasteur, accidentally makes the first attenuated vaccine. He was working on a cholera vaccine, and he told one of his students basically to do an experiment where you give cholera to a chicken, and the student forgot to do it for a month, and then said, oh shoot, I should probably get on this. Put the cholera in the chicken, and the chicken didn't really get very sick, but was protected from future challenges with cholera. So the first attenuated vaccine, it was weakened because it sat around for a month. It was discovered completely by accident, as most science is. 1882, you have the formation of the Anti-Vaccine League, and they start spreading a whole bunch of, I won't say fear rhetoric, but I kind of want to. They believed that smallpox was not spread by microorganisms, but by filth. This is because germ theory hadn't really caught on. The idea that you get sick because there are little, bacteria and viruses floating around. 1894, polio comes to the United States and causes a lot of problems. And then in 1905, in a really controversial decision, Massachusetts Supreme Court became the first to say it's completely legal to make smallpox vaccination compulsory. So everybody had to get vaccinated against smallpox. Generally, people don't really like being told what to do. And a couple of years later, this resulted in an angry mob storming one of these compulsory vaccine clinics and saying, you guys need to get out of here, and they ran them out of town. So things got really heated for a while. 1935, you had these two guys, Brody and Colmer. They tested the first polio vaccines. Basically, they just took a Lyme virus and they immunized people with it. We know that this doesn't work all that well, and not surprisingly, their results were catastrophic failures. Basically, everybody was paralyzed or died of polio. So this really fed into the anti-vaccine movement, because you had people like this doing stupid things that caused a lot of problems. 1950, probably one of the braver scientists, or stupider scientists that I've ever heard of. You had this guy, Hilary Koprowski. He developed a polio vaccine. It was an attenuated polio vaccine, and he first tested it on himself and his family. Luckily for him, it worked pretty decently, and it didn't cause a lot of problems. He then went into mental institutions, and without consent, he immunized a bunch of 20 institutionalized kids. So there was very little evidence that this vaccine actually worked, and he went in and forced these kids to have these things. Again, feeding into the anti-vaccine movement. 1952, finally somebody with some sense comes along. Jonas Salk. He developed another attenuated polio vaccine. Or sorry, this was fully killed. And this is the one that the government ended up buying a couple years later because it worked really well. It prevented infection in like 80 to 90% of the people that received it. Again, it was tested on institutionalized kids. Ethically, not so good. But it worked, which is a good thing. So the government bought it, licensed it, started distributing it in the United States. A couple years later, this guy, Albert Sabin, comes along and takes all three different types of polio, puts them in a vaccine, and that works really great. It's the one that we use now. And they're all dead. 1980, possibly one of the greatest achievements of humanity. We took smallpox and completely eradicated it from the world. There are absolutely no new infections of smallpox in the world, which is kind of cool if you think about it. And people have been trying to do the same thing with polio, but it's been, because of a lot of non-scientific reasons, it's been a little difficult. Unfortunately, in 1998, we had this guy, Andrew Wakefield. He was a British physician. He published papers saying that measles virus was found in the digestive tract of kids with autism. He then went on to suggest that there was a link between these vaccines, particularly the MMR vaccine, and autism. And he also recommended doing away with combination vaccines, so giving multiple things at the same time, and saying that they should all be given in single administrations. Let's just deal with the last point first, because it's perhaps the easiest to deal with. We said last week that you're constantly being infected by many, many things, bacteria and fungi and viruses that live in the world around you all the time. If your immune system was not set up to deal with lots of challenges at the same time, you would be dead. End of story. So the argument that giving a combination vaccine is somehow worse than giving an individual vaccine doesn't hold a lot of water scientifically. Additionally, I hope everybody understands that there's a really big difference between correlation and causation, right? Like, I always eat a bagel every Wednesday. It's not Wednesday because I eat a bagel. It may be, but probably isn't. So there's a difference between saying that there's an association between something and saying that it's causative. So this is really something important to keep in mind. After this paper came out, people said, ooh, this is really bad, vaccines are dangerous. We should probably not vaccinate our kids. Rate of vaccination for a lot of childhood diseases went down, and the rate of infection with measles and mumps and all those things went up. And it's continuing to go up to this day. In 2004, a lot of legal troubles came about. People realized that most of the patients that were involved in this study were recruited by a lawyer who was suing the vaccine makers. So there was a lot of ethical stuff going on. And the authors fully retracted the paper and said the conclusions were not valid. So they themselves admitted that they falsified the evidence. Boom, end of story, right? Unfortunately, when people think about this paper, they ignore that fact that it was taken back and that this guy was kicked out of medicine. And the rates of vaccination are still relatively low compared to what they were 20 years ago. And diseases are going up. So enough gloom and doom for now. How well do vaccines actually work? The answer is pretty darn well. So on the left here you have a chart showing the cases of morbidity, so sickness due to diseases that you can be vaccinated against. This is the cases in the year prior to the introduction of their vaccines. And then on the right is 2013, the number of cases of the disease. So you can see that most of these things that you can be vaccinated against have gone down more than 90% since the vaccines have come out. The one that's the weakest is pneumococcal disease. That vaccine only came out in 2006, so it hasn't had so long. So really they work really well, and there's no question that vaccines are a lot safer than the drugs that you would take to get rid of these diseases. I don't think anybody is really questioning that. So what actually goes into a vaccine? This is something that scares a lot of people out of getting them. There's 6 major things that you put in a vaccine. One, you need the active component, so the thing you're being immunized against. This can be the full pathogen. It's probably weakened, attenuated, or fully killed. It could also just be a fragment, like a protein or something like that, if we know what will give you immunity. Second thing is an adjuvant. Adjuvants are very common in immunology. They are normally bacterial components or viral components that activate innate immunity, which help adaptive immunity to become activated. So they really just give you a better immune response. People are really scared because the only FDA-approved adjuvant so far is alum. It's an aluminum salt. And it is well documented that high doses of aluminum over time will cause brain and bone disease. Not so good, right? Luckily for us, the dose of aluminum in vaccines, the vaccines that you give to kids, is 4.4 milligrams if you include all of the vaccines that you give in the first 6 months of life. Whereas the dose of aluminum that kids will get from breast milk during that same time is 7 milligrams. So you get half as much aluminum from vaccines. It's not a problem, quite safe. There's also antibiotics, which they use to keep the solution that the active components are in sterile. They're mostly removed by the time you get the vaccine. Then there are these stabilizers. They have really funky names, kind of scary names. Things like magnesium sulfate or sorbitol or monosodium glutamate. They sound like they should be bad, right? But every one of these things is commonly found in foods that you eat probably every day. And usually when you eat the food, you get a much larger dose of any of these things than you do in a vaccine. So the only thing that I may recommend not consuming on this list is beer, but like all the rest of it is probably fine, right? So if you're not going to stop eating these things, why would you be worried about it coming in through vaccines? Anyway, 2 other components, preservatives and trace components, whatever that means. It just means stuff that's left over from the production of the vaccine. So the preservative that everyone likes to go on the attack against is thimerosal, which is really ethyl mercury. So when people say mercury, you think of this like silver liquid thing that everyone knows is really dangerous, right? The problem is there's a big difference between this and thimerosal. Thimerosal is a mercury-based preservative. It's used to keep bacteria and stuff from growing in the multiple dose lots of vaccines, or vials of vaccines. It's present in very low doses, so 1 part in every 10,000 parts or less than that, is thimerosal. The law says there has to be less than 50 micrograms in every 500 microliter dose. That is a tiny amount. And in infant vaccines, there is no vaccine that has more than 24.5 micrograms. Most of them have 0. So just as a little demonstration, we have in this tube 50 micrograms. This is what 50 micrograms looks like. Oh, sorry, 500, it's 10 times as much. Because I was too lazy to mass out 1/10 of the amount to get 50. So you can pass this around. Just don't open it. It's completely safe, but don't open it so I don't lose it. So that's how much thimerosal there is in vaccines. It's
Or
really
10
small.
times less.
10 times less.
Yeah, 10 times less. Even that much wouldn't be that scary. Anyway, so it's ethyl mercury, right? People are concerned about mercury in fish. Fish have mercury. Hopefully that doesn't scare you. The mercury that you find in fish is in the form of methyl mercury. This is cleared from the body a lot more slowly than ethyl mercury, thimerosal. And studies that say that it's dangerous in fish are somewhat inconsistent. I found this completely random study that wasn't really looking directly at this, but in 1931, for reasons that don't make much sense to me, doctors decided that they would give patients a 1% solution of thimerosal. So that's 1,000-fold higher than what they're getting in these vaccines, right? Directly intravenous. So the most dangerous route that you could possibly think to give mercury, 1,000-fold higher than is in the vaccines. And none of the patients had any adverse effects. Probably safe, right? There's also formaldehyde in vaccines. People love to criticize that. There's 2 micrograms of formaldehyde or less in any vaccine. So it's not going to be possible for me to measure 2 micrograms. It's tiny. Also, formaldehyde is produced by your body in its normal metabolism. It's excreted in the urine very, very quickly. So it's not really that problematic. So hopefully I've convinced you that there's really not that much dangerous stuff in vaccines, despite some of the things having really scary sounding names. So now I promise the gloom and doom is totally over. No more of that. The future of vaccines, where are we headed in the future? There's some really cool stuff going on. Most of the vaccines that we have now are against infectious diseases that you get sick, you're sick for a month or something like that, you clear or you don't. Vaccines of the future are going to be against more chronic diseases, not just infectious, but also autoimmune or cancer or Alzheimer's. So the big 4 are tuberculosis, malaria, cancer, and Alzheimer's. A lot of money is going into all of those. And if you're really super curious, we can talk about how they're designing any of those. Another really big problem is how to immunize an aging population. So we know really well that that people of advanced age, no one like that is in this room.
Why do you look at me?
People of advanced age have a very different immune response.
Your father and I will have a talk tomorrow.
I heard nothing. The immune response works very different in people of advanced age. Memory cells don't last so long. It's harder to vaccinate them. So we really want to understand how we can lengthen the time that the vaccinations we give in childhood last later in life, right? Or how we can re-vaccinate later differently. HIV is another thing that people are dumping tons and tons of money into. But it itself presents a really interesting problem. Because even if we had today an HIV vaccine, there was a study that came out recently saying something like 25% of people would not take it just because they think they have absolutely no risk of getting HIV and the vaccine may cause HIV in their hands. Probably unlikely, but that's an important consideration of sort of a public health thing that scientists need to consider as well. And then finally, just so you don't think that pharmaceutical companies are actually all evil and terrible, some of them are, some of them aren't. There's a lot of push by both for-profit pharma and non-profit companies to develop vaccines against tropical diseases and things that you don't find in the United States. Things like dengue. Sanofi actually just recently licensed a dengue vaccine that has a really good efficacy. and then a whole bunch of other tropical diseases. People actually do care about these things, and it's very important that we develop vaccines against them, not only for the people that are suffering for them, suffering with them, but also if you convince your Congress people that we need to devote more money to this. You never know if somebody's going to bring, say, Zika virus to the United States and then cause an outbreak of a tropical disease or a rare disease that we haven't seen before. So, with that, I'd like to ask if anyone has any questions, and then, after we do questions, we'll move on to the Zika part of the topic. So everyone knows absolutely everything about vaccines. Awesome. Man, I knew I was good. I didn't know I was that good. Yeah.
How are they developing new vaccines for things like Alzheimer's and cancer?
Not well, is the short answer. So for Alzheimer's, the first vaccines that they were trying to make were against amyloid beta, which is the protein that deposits in plaques in the brains of people with Alzheimer's. As it turns out, those plaques aren't really that important for the pathology of the disease, so I don't think they're going to work that well. There's another protein called tau protein that people are trying to put in a vaccine. That might be better. I'm still not sure that that's important in the pathogenesis of Alzheimer's, but it seems like it might be better.
What's the process of actually making the vaccine?
Do you mean producing the vaccine or making a new vaccine?
Or producing the vaccine that we use?
I don't know every step. Most of them are proprietary generally. But you will package the agent, the infectious agent, in some sort of liquid, emulsify it in the liquid. It has to be sterilized, so that's why there's the antibiotics and stuff. And then you just put the preservatives in.
I heard like the egg.
So
Oh yeah, so some of them require...
It varies based on pathogen. So like flu virus and other viral things are grown in eggs because you can only grow a virus up until recently, you could only grow viruses in mass quantities in things like eggs. And so people who have egg allergies are advised not to get those kinds of vaccines, but bacterial ones can be grown up in some kind of bacterial culture. So there are variants, but nowadays a lot of the vaccines that are protein-based are grown up in other microorganisms in mass quantities or done synthetically. But actually, E. coli are used a lot to make synthetic compounds.
Which is why you need the antibiotics.
Yeah, and so you need to purify those compounds from the microorganisms that make them, and hence the antibiotics and the other preservatives. So really varies.
Yes?
How come some vaccines are long term and some are short term? How do they all stay long term?
The true answer is we don't have a really good answer for that. The hand-wavy answer is that the vaccines that last for a long time induce memory cells that last for a long time. So in order to survive, a T cell or a B cell needs to be activated a little bit. The general answer that an immunologist will give you as to why some of them last for a long time, even though so let's use chickenpox as an example. That lasts for a very long time. You don't have the pox virus in your body the whole time, but what's keeping these cells alive is probably like a bacterium in your gut or something that looks like the pox virus, so it can activate them a little bit. And likely the ones that don't last, there's multiple possible reasons, but it could be that there's not that mimicry going on, so you don't have constant active reactivation throughout your life. It could also just be that the vaccine formulation is not so good at inducing the memory cells to begin with. But it's an important question and one we don't have a great answer for.
And usually vaccines that provide long-lasting protection are also diseases that if you got them naturally, like chickenpox, you get it once, from our generation, we didn't have the vaccine, we got chickenpox, and usually we're protected from life, whereas other ones you can get more often. I think you mentioned this earlier, but whatever mechanism is that allows you to be protected from life, from getting sick, is similar to the vaccine, but it's not as clear yet.
Just to tag along that, I'm certainly of an age way before yours. We had pox parties when I was younger. They would bring all the kids, if one person came down with it, all the neighborhood kids were invited on, and they passed around lollipops And that's how they were able to get out of the neighborhood. There weren't vaccinations. You took the lollipop and then everyone got it, was done.
Right.
Little did they know that it stayed alive inside the body, and that's why the shingles virus that
Exactly.
presented itself.
Yep.
But they had no idea that that was going to happen at the time. My question was going to be about the flu vaccine. They have said consistently that they don't know next year's strain and why this year's vaccine will not be good for next year. How do they plan that?
So in the spring or the summer, they'll go out into animals, pigs and birds and stuff, and look at what variants of the virus are causing infections in animals and try to predict what will cross over to people based on that. It doesn't always work that well, it sometimes does, but you can get spontaneous events that cause dramatic changes in infectivity that make it very hard to predict. Like all of the pandemic strains, the strains that go pandemic are usually, you had a co-infection with 2 different viruses in one host, create something totally new when the genome recombines, and that's very, very hard to predict. But for the standard, relatively slow mutating viruses, you can get it kind of an idea.
So after getting them year after year after year, wouldn't you then be building up an immunity for virtually all of it?
Well, the problem is it changes relatively rapidly. Every time influenza replicates, there's one mutation. Literally every virion should have one nucleotide difference. So that's what prevents you from having lasting immunity. Although there is some protective effects. If you have a pandemic, pandemics tend to occur in waves of 3, with each wave being smaller because there's some lasting immunity. It's not great, but it prevents, 18 million deaths will go down to 500,000, will go down to 17.
Would it be possible for a live attenuated virus to get one of the mutations that you're talking about and then be passed to like someone else who, like maybe an immunocompromised person?
So probably not. It depends on exactly how the attenuation was done. And certainly, the trend in vaccinology is to move towards fully inactivated viruses now. We do still have, there are some cases where you require a pseudo-living organism in order to get protective immunity, so it's not possible to fully inactivate it. But the attenuated viruses and pathogens shouldn't be able to really replicate that much. I mean, you can't get sick from an inactivated flu vaccine, from an attenuated flu vaccine.
But can it be passed to like someone else?
I suppose theoretically, again, it depends. It's probably lot to lot, honestly, how well the attenuation worked. And it's probably pathogen to pathogen.
So there are 8 billion immune cells in our bodies. And of those, there's a whole bunch of different types of sort of classes of them. When we introduce either a real pathogen or an attenuated one through a vaccine, isn't it, it sounds to me like these cells are already sort of pre-immune to whatever disease that we might catch. But
Yes.
we die anyway if we catch the real disease. So I don't know if my question makes sense. Does that mean that there are some people that don't have any immune cells to some diseases? And if so, then what happens? Yeah, so that's the slide.
So probably the only case where that would happen is if a person was immunodeficient.
Okay.
Or just very unlucky. It is possible, because you only have a relatively limited repertoire of T cell receptors or B cell receptors, but highly unlikely. You should generally be able to create receptors that are specific for anything. Plastic, Mars rocks, like name something, anything. The problem is that naive cells that have never encountered their cognate pathogen, are not so good at becoming activated. So if you die before they become activated, you're cooked.
They also get stronger after they've
Yeah.
encountered the pathogen. They kind of replicate, and the cell itself will mutate to become better at recognizing that pathogen, and they can then form the memory cells And so, because they've seen it, it's sort of like, they're like predisposed to kind of be able to recognize it, but they're not, they haven't really learned how to fight it really well. So they sort of gain better skills at fighting those pathogens after they've seen it once.
The activation requirements of a memory cell are much lower than a naive cell.